All right, so next we're going to talk about how basically same type of calculation for a position, for a speed, and things like that. How we can do that using the energy approach, because one of the things we have here is when the surface is frictionless, then the only force acting on the system is the spring force, and we learned that spring force is a conservative force. That means we can use the conservative force to conserve energy. That means energy, mechanical energy is conserved when the spring system goes back and forth between x equals a and x equals negative a. That means back and forth, the spring is, conserving energy. All it does, it converts energy from one type to another, from kinetic to potential, from potential to kinetic, and there is no friction to dissipate energy. And so you have always same amount of energy. Total energy is constant for the entire time. And this graph represents how, for example, your total energy, which is that orange line, is in terms of kinetic and potential generally, right? You can say energy is kinetic plus potential. And what we have here is the energy, if you take the spring, pull it to the, x equals plus a and holding, energy at position A is purely potential energy. That means at x equals plus minus a, your energy is equals to k plus u, but it's equals to u because kinetic energy here is zero, since at position plus a and minus a, there is no velocity. Speed is zero, so there is no kinetic energy. And after that, as you let go the spring then converts at that potential energy, or the spring force converts that potential energy into kinetic energy every time it reaches the equilibrium. So that's why you can say, right, potential energy is zero at equilibrium. So all of that energy is now kinetic energy. So then kinetic energy then again converts back to potential energy when the spring system goes from x equals 0 to x equals negative a. That means the energy goes back and forth between kinetic and potential. So let's say here's what we have. Energy is conserved in a simple harmonic motion. Remember, the general equation is 1/2 mv squared plus 1/2 kx squared. But you have to understand that generally what we have is this. So kinetic energy is 1/2 m times v, but v is as a function of time. So technically it's negative omega a sine of omega t plus phi. And then potential energy is then it's a spring potential energy. So it's 1/2 kx squared, but x itself, right, is changes with time. So it's a cosine omega t plus phi. Okay. That means both kinetic and potential energy change with time. So that's why. See, this blue is the potential energy. It changes with time as a cosine function. Kinetic energy, it changes with time as a sine function. So all of those things change with time. But here's what we can do. So remember, energy is kinetic plus potential, which means I can write this as 1/2 m times then negative omega a sine of omega t plus phi squared, right? Because I am squaring the, so I forgot squaring this 2 over here, sorry. Because it's v squared and this x squared. So this is squared, then plus the potential energy, which is 1/2 k times then a cosine omega t plus phi squared. Okay. So we end up with this equation. Now, one of the things I'm going to do, I'm going to replace um, omega with, for example, square root of k over m. Remember this equation, or let me do the omega squared equals k over m. Because let me kind of write that equation over here. What we end up with this, if I'm again doing this, so energy is then 1/2 times mass times everything here is squared. So it becomes omega squared, and negative disappears because I'm squaring the whole thing. Omega squared, a squared, sine of omega t plus phi squared. Then plus 1/2 k a squared, then cosine omega t plus phi squared. Well, square is right here. And then I'm going to take omega squared that is right here and replace it with k over m. So if I do that, see what happens. If I replace this omega squared with k over m, then m's cancel out, and what I end up with is this. It's 1/2 ka squared for this term, which is then sine square omega t plus phi, then plus 1/2 ka squared here, then cosine omega t plus phi squared. Okay. If I factor out 1/2 ka squared, then I end up with this. Sine of omega t plus phi, sine square of omega t plus phi, plus cosine square of omega t plus phi. And if you remember your Greek, the trig identities, that equals to 1. That means total energy is equals to 1/2 ka squared, and that's what I have. So that's one of the ways we can write total energy of the system when it's purely potential energy. And this is how we can write very similar way total energy of the system when it's purely kinetic energy at the equilibrium position. That means kinetic energy is maximum at the equilibrium position. Potential energy is maximum at the x equals plus minus a positions. And that's why I can write this total energy in terms of either just purely kinetic, 1/2 mv max square, or purely potential, 1/2 ka square, or combination of both when the system is neither at x equals plus minus a or x equals 0. That means this is some random position where object has both kinetic and potential energy. So I can write it in terms of that. All right, so again, let me show you that simulation in terms of the kinetic and potential energies. All right, so not this one, but this one over here. So let's see what we have. So again, same spring system. See, right now it is at x equals plus a. Remember, right now the energy is purely potential. So I can say that energy is equals to 1/2 ka squared. That's the total energy. But remember, one of the things about kinetic energy and potential energy that you can convert one another, right? So that means the total energy at any point then going to be constant. That means if I take this point x equals a, and then this x equals 0, then I can say energy at those 2 points equals the same, exactly the same number, same amount of energy, which means it's going to be one place purely kinetic, another one purely potential. So that's when I can say it's 1/2 ka squared at x equals a position, or 1/2 mv max square, and that's x equals 0 position. But when the spring is somewhere over here, let's say, right, then this is basically also equals to then 1/2 mv square, and v is not the maximum, plus 1/2 kx square, and x is not 0, or plus minus a. Okay, but this is equals to that, or either one of them then equals to this, because the sum of kinetic and potential at any point is equal to the total kinetic energy. Okay, so and look at then the simulation. You can see that you have two graphs. One gives you the energy graph, which is in terms of kinetic and potential, and that's right here, this one over there. The other one is kind of like a pie graph, which is, let's say, in terms of where you have kinetic and where you have potential, and when you convert from kinetic to potential and things like that. So try to see that sort of like, let's say I have it run it slow a little bit, so you should be able to see it. See, when it goes to negative a to a, right? So at a, it's all potential, then kinetic, then potential, then kinetic, then potential, right? And you can even see the values and things like that where it's 0. So you can, maybe you can, like, let's say, slow it down even more. And then you can see in terms of when the potential energy is maximum, kinetic energy is maximum, and all of those things. But the idea here is, you can see, right, kinetic energy, potential energy, and you can even find a position where they're equal to one another, right? So let's say, not there, let's see somewhere over there, they're almost equal to one another. There you go. And then one converts to another other one. So this is, you can see, right, as the spring goes back and forth, then you have 100% energy converted from kinetic to potential and the potential to kinetic. That's why energy is conserved, and I can use any of those equations to describe that energy. All right. So We have maximum kinetic, when the kinetic is maximum, potential is zero, and when the potential is maximum, kinetic is zero, right? So then K plus U is constant. So we can again say this, right? K max equals U max. So that means, let's say this is, going to be always true. 1/2 mv max squared always equals to 1/2 Ka squared. We can cancel, let's say 1/2, and then just use that to solve some of the things. For example, then I can represent V max in terms of square root of K over M. But what is square root of K over M? Well, remember that's omega squared. Sorry, that's omega because square root, right? So that's why we have this V max is equals to omega times A. We already knew that from the previous few slides. All right, so then again, same thing in terms of all those variables, right? Coming back, that means omega is equal to square root of K over M. Frequency and period can be also related to those. Now, one of the things about this energy approach is it can allow you to find the position if you know how fast it's moving at that position, or you can find the position where or you can, let's say, find how fast it's moving if I give you some kind of specific position. That means it's, from energy, right? You get position and speed, kind of like those two things. Again, tell me what position you want, I can tell you how fast you're moving. Or if you tell me how fast you're moving, I can tell you at which position or positions you are moving that fast. So those are the things kind of like, let's say, we can get from this energy approach. Okay. All right. So here's an example. Um, Again, that example, I'm still going to do that. But the idea here is that there's some kind of, system in where we take the spring constant K to be 19.6 Newton per meter, amplitude 0.1 meters, and X is equals to 0.1 cosine 8.08 T, and velocity is 0.808 sine 808 T. So those are the things kind of like given to us. So we're going to determine the total energy, and then the kinetic and potential energy is a function of time. Then velocity when the mass is 0.5 from equilibrium, then the kinetic and potential energies at the half amplitude, which is X equals plus minus 8. All right, so that means what we get from here is some of the values that we already given. So let me write down for the X. So X equals, remember, A cosine omega T plus phi. So if I'm given this as negative 0.1 cosine 8.08 T, so this I'm given this for the X, and then for the velocity, I'm given 0.808 meter per second. This was meters. Then sine of 808 T, right? So I'm given those. Then I can use those then to get some of the information, like let's say, so in terms of the, which was part A, right? Asking the total energy. Okay. So let's look at then that part A. So total energy. Okay. Now we are given spring constant K and an amplitude, which is 0.1 meters. And I can say then total energy is equals to, remember, I can say it's 1/2 Ka squared, and those two already enough for me to calculate that. Or I can say it's 1/2 mv max squared, and using that and mass, I can also do that. But we are given the mass. No, let me see. All right, so the mass is given to us, not here, but in that original example. So it's 0.3 kilograms. So let's say we'll see that example still. We're not skipping that, but the idea here is, I moved it a little bit back because it required us to look at sort of like a vertical spring system. So we're going to talk about that in a little bit. So, but let's say the mass is given to us. So that means, I can use this. So for example, if I do 1/2 19.6 newtons per meters, then times 0.1 meters square, which is 1/2 Ka square, right? Then I can calculate basically my, total energy using this equation of 1/2 Ka square. And this will be 9.8 times 10 to the negative 2 joules. And again, I could have used 1/2 mv max square, also giving me the same thing. Part B, it says determine or find the kinetic and potential energy as a function of time. Okay, So that means I can use this equation where this is kinetic energy as a function of time, what I showed you in a minute ago. So it's 1 half mv as a function of time square. Okay. So that means, basically this equation over here. So then I can do this in terms of equals to, so 1 half 0.3 kilograms, then times, and I plug in 0.808 meter per second, then times sine of 8.08 t, and I square that. So then kinetic energy as a function of time will be 9.8 times 10 to the negative 2, then sine square 8.08 t. Same with the potential energy as a function of time, which is 1 half ka squared, sorry, x squared, when 1 half times k was 19.6 newtons per meters, then times the negative 0.1 meters, then cosine 8.08 t, then I square that. So then this is going to be equals to 9.80 times 10 to the negative 2, then cosine square 8.08 t. And that's what we have for the potential energy as a function of time. Part C is asking for us to find the velocity when the mass is 0.05 meter from equilibrium. Now, how do we find that? Well, here's then what I can do. See, remember, as I said, right? So you can solve for the velocity or the speed, technically, right? Remember, the energy approach doesn't give you velocity, it gives you speed because, it's a scalar quantity. So it gives you the speed, for a specific position, or it gives you position for a specific speed. Now think like this: position is 0.05 meter from equilibrium, and I want to know how fast I'm moving at that point. And I can use energy approach to get that a little bit easier than, let's say, those vector equations of motions. So what I do here is this. Let's say I know that if this is x equals 0 and this is x equals a plus a, right? I know what's the energy here, right? The total energy here, which we calculated there. That means the same amount of total energy will be at some position here, right? Where x equals 0.05 meters. That means energy, the total energy is equals to energy at point A and also energy at some point X. The only thing that energy at some point X is equals to 1 half mvx squared, then plus 1 half kx squared. Where right now I am given that X, and all I need to do is to find that Vx, because this sum is equal to the total energy, which is equal to the same as total energy at point A, which means 9.8 times 10 to the negative 2 joules, that's the total energy, and it equals to 1 half, then 0.3 kilogram times Vx squared, then plus 1 half, 19.6, that's for the K, and then 0.05 square, and that's for the X. That means I have everything but the Vx, and I can solve for this Vx, where if I continue over here, so then Vx will be equals to 0.7 meters per second. Okay, you can try then plug in and rearrange, and you will see that's basically what you're going to get. All right, so finally, the last one is let's find the kinetic and potential energies at the half amplitude. All right, so I'm going to have to clean up a little bit here. So what I can do here is, let me clean up for this part B. We don't really need this part B, okay, because we need part A. That's going to be useful for us. Okay. Okay, now, what I have here is then this. This is for part D. It says kinetic energy and potential energy at half amplitude. Now, what I can say is this. Kinetic energy, potential energy is equals to 1 half kx squared, but then I can say it's 1/2 k times, what is a? Well, a is 0.1, and so it's half of that. So that means I can write this as 19.6 for k, and then 0.05 meters square. And that will give me 2.5 times 10 to the negative 2 joules. Okay. Now, how about kinetic energy for that position? So here's what I have. I've seen sometimes students wrongly assume that if it's a half the amplitude, that means kinetic energy should be half the potential energy, or basically will be exactly the same as potential energy, which is basically then total energy will be exactly half kinetic, half potential. Okay. But we can see from here that's not quite the case. So kinetic energy, for example, I don't know how fast it is moving at that 0.05, which I can find it using, again, the same method that I used in part C, but I can do it a little bit easier because kinetic energy, remember, plus potential energy equals the total energy. I just calculate potential energy at that amplitude, and I have the total energy. All I have to do here is just say K is equals to total energy minus potential energy, and I can find the kinetic energy, which is basically 9.8 times 10 to the negative 2 minus 2.5 times 10 to the negative 2 joules. So then kinetic energy will be 7.3 times 10 to the negative 2 joules. And you can see, right, it's not equals to the potential energy, it's not exactly half. So it's not half kinetic, half potential, at half amplitude. Well, you actually have much more kinetic energy than potential energy at this point. All right, so that's for this example. All right, so over here then I kind of have, in terms of looking at all this as vectors. So remember, so this is being the x equals 0, this is x equals a, some of the things we already talked about. So if I'm looking at this position x equals plus a, remember velocity was 0, acceleration was negative and maximum, right? And the force was maximum and negative. And then I said, right, so when you go to the x equals negative a, then again velocity is 0, acceleration is maximum but positive, then force is maximum but positive because force and acceleration now pulling the system to the right where the equilibrium is. And at the equilibrium, there is no acceleration, no force, because remember, F is equals to kx. And if x is 0, F is 0, and F is 0, acceleration is 0. But then the V is the maximum, right? V is the maximum, is maximum speed, right? Then the direction, right or left, depending on which direction it is moving. But that's kind of what we have. That means that x equals 0, there is no force, there is no acceleration, even if it's just going through that point, right? So at the instant when it's passing equilibrium position, there is no acceleration, no force. Because as soon as that passes to the other side, it changes direction and it starts increasing. So that's why we have this acceleration, which I already given you the equation here, just basically we're skipping a little bit until this point to get the acceleration. But remember, it's a derivative of the velocity as a function of time, and we end up with negative omega a omega squared a cosine omega t, and maximum, this is ax equals negative omega squared x, and the a max is then just omega squared times a. That's for the a max. The acceleration is proportional to the negative of the displacement, so that's why this is a simple harmonic motion. Remember, right? I mentioned that why this motion here is simple harmonic motion, because of that. Acceleration is negative of a proportion to the negative of the displacement. Every time your system has that, then its motion is a simple harmonic motion. So again, if you take the spring and if you move it to the right, stretch it and then you let go. So the spring here, spring force equals negative k times delta x. And since spring here, force is equals to mass times acceleration, that means you have this, right? Negative kx equals mass times acceleration, and a equals negative k over m times x. I already mentioned this, right? So this ratio is known as omega square. So then you can rewrite this as ax equals negative omega squared times x. And angular frequency, omega equals square root of k over m. All right, so that means the simple harmonic motion, again, only when acceleration is proportional to the negative of x. And the spring system and the pendulum systems are both, you know, uh, basically are simple harmonic motion because, you get this proportionality. Okay. Now here we can have spring that is hang vertically rather than on a horizontal axis, but still, kind of like similar idea. The only thing here is usually when you have a spring hang vertically like this, it's a very, easy way of finding the unknown spring constant K. For example, imagine you have a spring and a block attached to that. So basically sitting like this, right, in equilibrium. So one of the things we have here is this. So let's say, or let me show you in terms of this. So let's say first we have the spring. So let's say this is just the spring on itself. So let's say this is the spring like that. And then I attach the block. And when I attach the block, then the spring has a force now acting on it, which is equal to the weight of the block, F of G. And it's gonna, stretch the spring. But as soon as the spring is stretched from its unstretched state, then there's also, that means this is, let's say this is the, gravitational force. There's then also the spring force, which, starts increasing because spring force equals to negative K times displacement, which is, let's say I can say delta Y. Now, as it goes from this position to, let's say, over here, right, eventually the spring force matches its strength in terms of gravitational force, right? It matches the spring force, the gravitational force in its magnitude, then they equal to one another. Because otherwise it was gravitational force plus the spring force then equals to mass times negative acceleration, because the spring force was smaller, but then it says it increases as the block stretches more. Eventually they equal to one another, and then this is equals to 0. And then the system comes to rest. So that's why, for example, then here you have a system that is basically at rest because it basically goes down until the spring force matches the gravitational force and system comes to rest. Then in that case, I can say then the spring force equal to the gravitational force. Well, what is spring force? Well, is K times delta Y. Let's say looking at their magnitudes are equal to one another, right? So the spring force is K times delta Y. Gravitational force is just mg. Then I can relate those things together because I can say then delta L equals mg over K, or K is equals to mg over delta Y. So that's why right now in the experimental labs, what we can do here is we can have a spring in equilibrium, just unstretched, let's say a spring, then attach mass, known mass, right? And then stretch it a little bit, measure that stretch distance, delta Y, or delta L if you want to call that, and then do the ratio, right? So basically mg over delta Y will give you the spring constant K. Okay, so this is basically uses delta L because technically you're going down, so the delta Y itself is negative, right? Because you're going below the 0 line, so you can kind of do that. But in that case, you have to include the negative, because remember the K itself can never be negative. It's a positive quantity. Spring constant is always a positive quantity, and that's what I have over here. So this was the famous example 4. So, but I moved it here because we are in a way looking at this as this is the spring. All right. So actually I made a mistake. I thought this is vertical, but it is horizontal. But anyway, so let's look at that example anyways. So I have a spring that stretches to 0.15 meter when a 0.3 kilogram mass is gently attached to it. The spring is then set up horizontally. Oh, so that's what I'm talking about. The spring is then set up horizontally because first we have a spring hang vertically, and we have then 0.3 kilogram attached to that. So then that 0.3 kilogram stretches it to 0.15 meters. And then we take out the setup and set it up horizontally. But this first sentence, this is basically when the spring is still, hang vertically. Okay, so then the spring is then set up horizontally with the 0.3 kilogram mass resting on a frictionless table. The mass is pushed so that the spring is compressed to 0.1 meter from the equilibrium point and then released from rest. So then we're going to determine the spring stiffness constant K and angular frequency omega the amplitude of the horizontal oscillation A, the magnitude of the maximum velocity, the magnitude of the maximum acceleration, the period, frequency, displacement x as a function of time, and the velocity at t equals 0.5 seconds. A lot of things to do. But the idea here is this: we have a spring that we don't know the spring constant k. We're not given, but we were told initially that, let's say here's a spring. Then what we do, we attach a mass, and then when we attach a mass, the spring is stretched to this, displacement of delta y of equals to, let's say, negative 0.15 meters, because it is basically then, as I said, right? So this is being the block, first it exerts force, equals to its weight, mg, but then the spring force eventually, increases until it reaches the same value as the gravitational force. Then here I can say then spring force, which is k times delta y, negative k times delta y, is equal to the gravitational force, which is mg. So because like this, then I can use it to find the spring constant k. K is equals to negative mg over delta y. So negative 0.3 kilograms times 9.8, then divided by negative 0.15 meters. Negative because delta y is negative, right? So again, negative then going to cancel out. I'm going to get 19.6 newtons per meters. That's where this spring constant K of the previous few examples come from. All right, so now that we found the spring constant K, which was for part A, right, to find the spring stiffness constant K, and we're going to be able to then use this to find the angular frequency. We can find angular frequency because we have the equation that relates angular frequency, right, to the spring constant K and the mass of the block. So again, this was part A, but we're still doing this. Omega is equal to square root of K over M. So square root of, now it's 19.6 over zero point 0.3 newtons per meters, kilograms. So we can find this to be then, what we've been using, 8.08 radians per second. And this is the angular frequency. All right. We also need, we got it. So part B says the amplitude of the horizontal oscillation A. Well, remember, after this, we take the system and, set it up horizontally. So then we stretch it from equilibrium, right, to a position where this is then 0.1 meters. And we're told, right? So, sorry, actually we compress it, my bad. So we compress it to that. Okay. That means that's my amplitude. That's part B, right? That's my amplitude, which is 0.1 meters. That's an easy one. Part C says find the magnitude of the maximum velocity. Okay. Well, that's also easy enough because Vmax now will be omega times A. I have omega 8.08. I have A now. Oh, I don't know why it does that. I apologize. So, and this is 0.1. So I can find Vmax, which will be then 0.808 meters per second. All right, so then part D says find the maximum acceleration. So I can also do that because A max is equals to omega squared times A, which is 8.08 squared times 0.1 meters. And I can find this to be 6.53 meters per second square. No, okay. Then for part E, it says the period and frequency. All right, those are also now hopefully will be easy for you because I can calculate that several ways. So I can say then, for example, period is equals to 2 pi square root of m over k, or I can say that this is equals to 2 pi over omega. Either way is fine. For example, I can probably use this 2 pi over 8.08, a little bit easier to do that, but same thing. If I do that, I'm going to get 0.777 seconds. Then frequency, again, you can calculate number of ways, which is omega over 2 pi, or just 1 over the period. Either way, just plug in and get 1.2 hertz, which is basically probably easier to do 1 over the period, right? The last one, which is find the displacement as a function of time. Oh, that's not the last one, so F. And this one I can, look at it in terms of x as a function of time is equals to a cosine omega t plus phi. Remember, phi or phi naught is the same thing for me, right? So basically the phase constant. Well, is the phase constant 0 or not? Well, it's not, because remember, we are starting at position x equals negative a rather than x equals a. How do we find that? What is the phase constant? So here's what we do. We say, okay, so x when t is equals to 0 is equals to negative a, right? So that's basically the position that we're starting from. And this is then equals to a cosine omega times 0, because that's t equals 0, then plus phi, which give us then a cosine phi. That means I have negative a equals a cosine phi. Well, from here, I can cancel the a's, but what I end up with is negative 1 is equals to cosine of phi. Then if I solve for phi, which is cosine of negative 1, what I get for phi? I get pi. That means my phase constant is pi. So then as x as a function of time is equals to, then I can write, okay, amplitude, 0.1 meters, then times cosine of, well, omega t is 8.08 t, then plus the phase constant, and that's pi. And that's my basically part f, right, which is the function, the displacement as x as a function of time. That means that's my, x. And we needed to find the phase constant phi. The last one, it says the velocity at 0.150 seconds. All right, so for that, I'm going to need to get some, room for that. And let me get rid of this because we already have the spring constant K and we have the, angular frequency values. So for that, what I'm going to do is remember that velocity is equal to just dx dt. Then derivative of that, right? So it becomes negative omega a sine of omega t plus phi. That means this is going to give me, so again, v as a function of time is then going to be negative. Omega is 8.08. Then a is 0.1. Then sine of 8.08 times t, then plus pi. And then this is then for specifically when v at the time of 0.15 seconds. That means all I have to do is come back here and then this to 0.15 seconds and then calculate the velocity. And I'm going to get negative 7.56 meters per second. And that's basically the speed at that velocity, right? It's negative, right? Basically at that instant of time. That means it's moving at 7.5 meters per second, 7.56 meter per second. Oh, sorry guys, my bad. It's 0.75. 0.756 meter per second heading to the left. All right. All right, so let's continue. By the way, I highly recommend you guys watch the video lectures and look at the lecture notes because I have a lot of lecture note, let's say quick checks that I don't go over here. If you remember, I mentioned that in the first few lectures. Then because I want you guys to look at those quick checks yourself. So basically watch the video lectures, try to understand everything, like let's say take notes and things like that. Then go to the lecture notes and look at the lecture notes and try to get those quick checks on your own, okay, using all those things that you learned from the lecture. All right, so next is the pendulum. So we got to the pendulum, and the pendulum is basically, again, is a system that has a simple harmonic motion. Because one of the things we have here with the pendulum, you take the pendulum, where let's say the pendulum sitting here in equilibrium, and we're going to start with the simple pendulum, whereas a simple pendulum has a length L. Basically, it's an object with mass m attached to the end of a light string that is fixed at some kind of pivot point, and the length L is the length of the string, which then you have the object, and the mass of the string is basically negligible because it's a light string, let's say. So the only mass in the system is the mass of what we call a pendulum bob, and m is basically the mass of the bob. And then you take this, so this is being, let's say, the system in equilibrium. Then you take it and move it some angle theta from it, right? And this means equivalent to, let's say, taking the spring system to stretch or compress. And then if you take it and move it some angle theta from the equilibrium, it's kind of similar to move it some position plus A. The forces acting on the pendulum system at that instant are tension, I'm going to put like F of t, and then the gravitational force. But the tension always perpendicular to displacement, so we don't necessarily use that as a force making the system, go back and forth, because what makes the system go back and forth is actually the gravitational force, mainly the component of the gravitational force. So this component, tangential component, which is equals to negative mg sine of theta. So the negative mg sine of theta then equals to mass times acceleration. That's basically Newton's second law, which means then what I can do here is I assume that as the system goes back and forth, it behaves like a simple harmonic motion. And remember, the acceleration is what? Is second order derivative of the position. Here, the position taken as an arc length. So that means d square s dt square. That means this portion, which is mass times tangential acceleration, can be replaced with d square s dt square, where then, I can just cancel the mass from both sides. That means d squared s dt squared is equal to negative g sine theta. But this doesn't seem like, where the s here is the, let's say function, and I'm taking derivative because I don't see s over on the right side. But here's the thing, there is an s on the right side, which is the arc length. And that's because we have this relationship, if you remember, the arc length is equals to L, radius or length times the, the angle theta. So S equals L times theta. Now, still, I don't have S, I don't have theta, I have the sine of theta. But what we do here is this. There is what we call a small angle approximation, where the theta, if the angle is less than 10 degrees, sometimes even less than 5 degrees, then sine of theta is approximately theta. So then the sine of theta can be replaced with theta. So you can see that then mg, the right side of the equation, where negative mg sine theta becomes negative mg of theta. And I can say this negative mgl times s. That means, this s, which is equals to L times theta, can be used to, if I go back on this slide, right, see it's negative g sine theta, or equals to negative g times theta. But then using this, I can say then theta is equals to s over length. So it becomes negative g over L times s. That means my equation is this, d square s dt square is equals to negative g over L times s. And you can see, right, g over L is the proportionality constant. And then what I have here, I have some function s. I take the derivative twice, and I come back to the same function with the negative sign and times some constant. And that's what we have. So that constant here, remember, so this is then equals to, let's say, d square s dt square times m. So then if I cancel the m's, then this coefficient in front of s is nothing but, again, omega square. Then I can say then d square s dt square is equals to negative omega square times s, where omega for the pendulum is the coefficient in front of the s, which is in this case, becomes, so omega square is equals to g over L, or they taking the square root of both sides, we end up with this. Omega equals 2 pi f equals square root of g over L. That means angular frequency is equals to square root of g over L for the pendulum, but also, see, this is for the pendulum. And remember, for the spring, it was equal to square root of k over m. That means this is for the spring, and this is for the pendulum. And you have different, things that pendulum or the spring, right, where the angular frequency depends on. So in this particular case, the angular frequency is in terms of square root of g, which is the acceleration due to gravity, always just 9.8, divided by the length of the string. Okay. So then, interestingly enough, what I can do from here is this. So you can see, right, if I relate those things together, then I can say then frequency is equals to 1 over 2 pi square root of g over L, or I can do for the period, which is 2 pi square root of L over g. That means those are the, the frequency and period for the pendulum. And you can see, right, for the frequency and period for the pendulum, the only thing it depends on, those things, those quantities depend on the length of the string, not even on the attached mass. So let's say if you have a simple pendulum, you displace it to some amplitude, and this doesn't even depend on the amplitude. Doesn't matter how far you displace and you let go, the period of oscillation only depends on the length of the string, not on the amplitude, not on the mass of the pendulum bob, but just the length of the string. You make half the length of the string, the period is basically decreases. You make longer string, period increases. How much mass you put, you take out and put an elephant on the end of the string, you're still gonna get the same same period if the length is exactly the same. So that's the important thing about this particular, the pendulum. And this is not a simple pendulum, and we don't really cover it as greater detail, let's say, as the spring, because most of the things that for the spring can be applied pretty much here as well. Okay. So I have an example. So it is said that Galileo discovered the basic principle of the pendulum, that the period is independent of the amplitude, as I mentioned, by using his poles to time the period of swinging lamps in the cathedral as they swayed in the breeze. Suppose that one oscillation of a swinging lamp takes 5.5 seconds. How long is the lamp chain? All right, so let's look at then what we have. I have a picture over here, something like, so this is we can model the swinging lamp as a pendulum like that. And one thing we can do here is, given that the period is 5.5 seconds, this is already enough for me to calculate the length of the string, assuming that G is also 9.8 meter per second square. Because one of the things we can do here is this pendulum as a system always can be used by geologists to measure the acceleration due to gravity at different altitudes. Maybe you can take it, go to the top of the mountain and use a pendulum to find the period. And period will be different than what, let's say, the geologist would measure at the sea level, because the gravity will be different. So we can compare and find the gravity acceleration at that particular location. But let's say this is the sea level, G equals 9.8. Then I can use this period equation, which is 2 pi square root of L over G, to find the length. What we do here is we square both sides. So then this is equals to 4 pi square, then L over G. That means I have T square is equals to 4 pi square L over G. Rearrange, then L is equals to T square times G over 4 pi square. So this is then 5.5 seconds times 9.8 over 4 pi square. So then the length will be equals to 7.5 meters. That's the length of the string. Next, what we have for part B is this. What maximum speed does the lamp have if its maximum angle for the vertical is 3 degrees? So there's a degrees. All right, that means if it's swinging maximum at 3 degrees from, let's say, its equilibrium position, how fast will it be moving at the lowest point over here? That means we know one thing, right? So it's going to oscillate back and forth like this, where the speed here at point 0 is 0, and point 1, which is the bottom of that, which is basically equilibrium, this will be moving with the fastest speed. And we want to know what is that speed. All right, so then how do we do that? Well, the easiest way to do it is using energy method. Because all I need to do here is this. Because the only force acting on it to make it move is the gravity. And it's a conservative force. Energy is conserved. That means kinetic energy of 0 plus potential energy of 0 is equal to then K1 plus U1, where this is 0.0 and this is 0.1. And it's going to start from rest at 0.0, and then 0.1 is my reference position, so there's no potential energy. That means all I have here is this potential energy at 0.0, which is this given in terms of mgh. This is equal to then kinetic energy at the bottom, which is 1/2 mv squared, like that. Now, I can cancel the mass because mass is unimportant in this case. And then V1 is equals to square root of 2gh. Rearrange, that's what I get. Now, the question is that, what is h? How high is basically the 0.0 relative to the 0.1? Well, in this point, what we're going to do here is this. taking, when the system was here at the bottom, right, point one, now it moves 3 degrees in this direction. That means move 3 degrees right above like this. That means this is basically 3 degrees. So this is the length and this is the length, right? So then what I can do here is this. Because I know that this is the length of the string, and when the string has been, or the system has been displaced by 3 degrees, then its projection here, which is right here, is L cosine theta. Because this is, we can say, right, L is the hypotenuse, T3 is a degree, so that this portion over here is the adjacent side of the triangle, which is L cosine theta. That means I can then solve for this portion by doing L minus L cosine theta, which means that L1 minus cosine of theta. And this exactly equals my h, because this is basically my height. That means this is equal to square root of 2 times 9.8 times, so basically for h, I'm doing L minus L cosine theta, or L times 1 minus cosine theta quantity, because I have L, which is 9.5 meters, then 1 minus cosine of 3 degrees. I can do that, and I can solve for V1 as 0.45 meters per second. Again, we are using this where h is equals to L minus L cosine theta, or factor out L, and that's basically for our height. All right, so we also have what we call a physical pendulum. So the physical pendulum basically is a solid object. It's a rigid object. So you can write any solid object that swings back and forth under the influence of gravity can be modeled as a physical pendulum. So the gravitational torque for small angles, which is less than 10 degrees, is given as negative mgl times theta, where this is that, so this is that axis of rotation, and this is the center of mass, and the gravity, remember, acting at the center of mass. So then what I can do here is I can say that L is the distance of this axis of rotation with respect to center of mass, L, right? And then, the theta here, the angle that it makes, right, when, rotating. And D here is basically that moment arm, right? Moment arm of the gravitational torque. All right, so then in a way, what we have here is this. So the torque, due to this gravitational force, is given in terms of its magnitude, right, times L, which is the distance, then remember times sine of angle theta, but we can say that sine of theta is equals to theta. So then just becomes, magnitude times distance times theta instead of sine of theta. So it becomes negative mgl times theta. Okay, it's negative because remember that for the oscillation, right? So you have the torque or the force proportional to the negative of the displacement. So plugging this into the Newton's second law for the rotational motion, which is where torque equals I times alpha, we can find that equation for the simple harmonic motion with omega equals 2 pi f, or it equals to mgl over I, which means that, remember that, and, this is mgl theta. So that means, I can say negative mgl theta is equals to I times, and then alpha, which I'm going to rewrite as d squared theta over dt squared, right? So if I do that, then I can say, all right, so then negative mgl over I times theta equals d squared theta dt squared, which is the second order derivative of theta is the negative of the theta times some constants. And again, what is that constant? That constant is omega squared. That means omega squared is equals to mgl over moment of inertia. Taking the square of that, both sides, that's my omega. That's why angular frequency for a physical pendulum is mgl over I, which is different compared, right? Quite different compared to the, a simple pendulum, which was just basically square root of, G over L. All right. So again, so this is basically what we have for the moment, there's a moment of inertia also it goes into play and things like that. So that's why this is a physical pendulum, and you need to, even more complicated because there's a torque, there's a center of mass, all that information has to be taken into account. All right, so I do have an example here where we can see. So we have an easy way to measure the moment of inertia of an object about any axis is to measure the period of oscillation about the axis. Suppose a non-uniform 1 kilogram stick can be balanced at a point 42 centimeters from one end. If if it is pivoted about that end, it oscillates with a period of 1.6 seconds. What is the moment of inertia about that end? All right. So then what we can do here is we are given the mass of the stick. We're given that, remember, this is basically our L, right? And we are given then the period. So then we can use the equation that we just learned where omega is equals to square root of mlg over moment of inertia. But we're given, period, but we know that angular frequency is 2 pi over the period. So I can rewrite this as period is equals to, right, 2 pi, then square root of moment of inertia over then mgl. So basically I have this equation. All right, again, what I do, I square both sides. So then the t square is equal to then 4 pi square, then moment of inertia over then mgl. And remember, our goal here is to find moment of inertia. So then I is equals to, then this is t square times mgl over 4 pi square. So then I have 1.6 seconds square times 1 kilograms times 9.8 times 0.42 meters, and this is divided by 4 pi square. Okay, so what we get here is 0.27 kilograms meter square. That's for the moment of inertia. This moment of inertia is 0.27 kilograms meter square. Okay, there you go. All right, so we kind of get rid of this to see what part B says. So for part B, then what I have is this. What is the moment of inertia about an axis perpendicular to the stick through the center of mass? Okay. All right, so this was part A. This was part B. Now, the idea was this. So this is was the moment of inertia with respect to basically this pivot point, right? And what I can do here is if I want to find then the moment of inertia with respect to basically the center of mass, that means, this is my axis of rotation, right? That's my pivot point. I can use the parallel axis theorem, where moment of inertia for some off center, pivot point is equals to I center of mass, then plus m, L square or H. It was H square, but we can put like L square. And this is what I just calculated, right? I is the moment of inertia with respect to the pivot point. So then I can rearrange this into then I center of mass equals then I of center point minus m L square. And I just calculate that, which is 0.27 kilograms meter square minus, 1 kilogram times 0.42 meters square. And I just calculate moment of inertia with respect to the center, which is 0.009 kilograms meter square. So that's moment of inertia with respect to the center of mass. All right, so this was for the physical pendulum example. The last thing we're going to talk about in this chapter is then what we call damped oscillations, which means going back to that, for example, spring system. Now there's a friction. If there's a friction, then that means there's another force, right, acting on the system that dissipates, energy. That means it's acting as a drag force. So you can say, right, an oscillation that runs down and stops is called a damped oscillation. Obviously, if there's a friction, the spring, going to start, going back and forth, but each time, reaching less distance than before until it eventually stops. So one possible reason for dissipation of energy is the drag force due to air resistance, or let's say the friction and things like that. So the forces involved in dissipation are complex, but a simpler linear drag model is where this force D, right, this contribution from this equals negative B times velocity, where B is some kind of constant, that we can use. So B times V. So this is model of a drag force. So then the idea here is my equation now, you know, sorry. So then force, net force equals then, let's say mass times acceleration, right? So the net force equals mass times acceleration. But in this case, right, so what I have is there's not just, spring force, but also this drag force. All right, so the left side of the equation, the net force, is now in terms of things like this. So it's the drag force. Okay, so the drag force, then plus then the spring force, then equals mass times acceleration. So, and that means this is basically, so the drag force is negative B times V. Then the spring force is negative Kx. And this is then equals to mass times acceleration. That is negative PV minus Kx is equals to mass times acceleration. And in a way, what we end up with is this. So think like this. So this on the right side is mass times d square x dt square. So then the first one is negative b times what is v? Well, this is dx dt minus then kx. That means if I rearrange everything, let me write down over here. So I end up basically with this. It's m times d square x dt square, then plus b times dx dt, then plus k times x equals 0. Okay. So now dividing all sides by mass, kind of getting rid of this. So we end up with something like this, which is then end up being an equation that I'm going to need to use for the damped oscillation. Okay, so this is basically the second order differential equation. And if I do that, what I will get here is this equation over here. Okay, you can probably see the derivation in some textbooks, something like that. But mostly we kind of like, let's say, give the solution. So the solution for that function is that x as a function of time is equals to, we had that a cosine omega t plus phi for the simple harmonic motion, right? For the simple cases. But now we have, because of this second term over there, then we introduce this, e to the negative bt over 2m factor, which then makes sure that the system basically eventually slows down and stops. Okay, so this is for the damped oscillator. And angular frequency now is, instead of being square root of k over m, now it's square root of k over m minus b square over km, which now I can say then omega naught is the original frequency, which is square root of k over m. So then I can say that this is, in terms of omega naught square minus b square over km, 4 over m square. That means now we have an angular frequency. Sometimes I just put like omega prime, so you guys know this is a new angular frequency for the damped oscillator. And this is the simple, original, let's say, angular frequency for the undamped oscillator. And you can see, right, the difference here where the b equals 0. That means this term, right, for the some kind of resistor or dissipative force is 0. Then you have end up with just square root of k over m. That means our motion basically now eventually goes to 0. That means, like, let's say the spring, you can see over here, right, as it starts from A, goes, and even it doesn't even reach negative A in the first time because it slows down, then comes back and moves less and less and less, and you can see, right, less and less and less until eventually basically comes and stops. Okay, so then our amplitude, or the envelope amplitude decays exponentially, where x max equals a e to the negative bt over 2m. That means this is position versus time graph for a damped oscillator. Undamped, you basically go like this, right, for forever. For the damped oscillation, you eventually slow down and you stop. All right, so damped oscillator has a position x equals x max cosine omega t plus phi naught. That means we can take the x max, right, to be a e to the negative bt over 2m. So now we have technically then several scenarios where we can use, right? So you can see, right, the slowly changing function x max provides a border to the rapid oscillation, and it's called the envelope. So the figure shows several oscillation envelopes corresponding to different values of the damping constant B. See, when B equals 0, that means you just basically stay there as a function of time, right? That means your amplitude, sorry, it doesn't change like that. Okay. So this is just basically the, simple case that we've seen in the beginning. When B equals 0.03, then, it kind of goes like this until it eventually stops. When it equals to 0.1, then it, goes down much faster. And you can see, right, 0.3, that means as the B increases, then your ability to kind of oscillate becomes very small. That means you just basically slow down pretty much right away. And then within, let's say 20 seconds, you go to 0. Here within, maybe like 100 seconds, here you can take it longer, and so on and so forth. That means, greater the value of B, faster you come to rest. Okay. So then this is known as kind of like exponential decay. So it occurs in a vast number of physical systems of importance in science and engineering. That means, this is a system where eventually, like same thing with the pendulum, right? So if it's a physical pendulum, there's a friction where there's an axis of rotation, right? Eventually comes to rest. So mechanical vibrations, electric circuits, and nuclear radioactivity all exhibit exponential decay. So all graphs have something like that, right? So U is equals to amplitude times some kind of exponential, negative exponential, which means that it comes and, slows down and stops. Remember, E is the quantity is 2.71828 is Euler's number. So X is the exponential function. V naught is called the decay constant. Okay. And simple harmonic motion now becomes, let's say, in terms of like damped oscillation, right? So then you do have this type of decay. In terms of then, same thing, right? For the mechanical energy, so it's no longer conserved, obviously, because you don't have the same constant energy since there's a friction who dissipates energy. That means, mechanical energy is no longer conserved, and the friction eventually dissipates until it's pretty much 0. So you can say, right, then E as a function of time equals 1/2 k x max square. And because now x max is, has an exponential decay function in it, so that means you just basically end up with original energy times e to the negative t over tau. This tau is known as a time constant. That means how long does it take for the system to decrease? You can see, right, energy has decreased to 37% of its initial value at t equals tau time. That means, there's a 63% decrease in energy in this time t equals tau. That means you only end up with the 37% of original energy. So this time constant is true for any type of system. It always represents the amount of time it takes for the system to lose 63% of its energy. So that's why it's a constant, time constant. And in this case, you can see, right, it is equal to the mass of the system, mass of the block, right, say, divided by this constant B. Okay, so this factor B. All right, so then oscillators' mechanical energy decays exponentially with this time constant tau. That means t equals 2 tau, you have only 13% of the original energy. That means 87% of the energy is gone. So at times tau, 63% gone, 2 tau, 87% gone. So it kind of gives you a way of, calculating the number of energy that you have left, amount of energy. All right, so let's look at this example. So we have an oscillator with the mass of 500 grams and a period of 0.5 seconds, has an amplitude that decreases by 2% during each complete oscillation. If the initial amplitude is 10 centimeters, what will be the amplitude after 25 oscillations? All right, so let's see what we have here. All right, so we are given, remember, the x max is equals to a e to the negative t over tau, or I can say a e to the negative, remember, the becomes bt over 2m. So then from here, what I can do is basically use this to calculate. So you can see, right, so from here, okay, oh, sorry, I have it's 2 tau over here rather than tau. Let me kind of rewrite this. It's t over 2 tau, okay. That means, for example, then if I kind of use this equation over here, I have x max equals a e to the negative t over 2 tau. And then in order for me to kind of get that information about, the time and things like that, I need to basically, or the tau, right? I need to, take a ln of both sides. Okay. So maybe let's do this first. Let's take that and divide both sides by a. So then, x max over a then is equals to e to the negative t over 2 tau. Then we're going to take the ln of both sides. So then I'm going to get then ln x max over a. And on the right side, then I'm going to get negative t over 2 tau. Okay. So then I have equation, remember, x equals x max, then cosine omega t plus phi, phi or phi naught. So, and what we're told here is, so we're given, remember, given the mass, we're given the time, which is 0.5 seconds. Okay. So remembering that basically this is the general equation. Now I can, now that I use this guy over here, I can come back and look at some of the information that I'm given. So mass is 500 grams and the period is 0.5 seconds. And then it says that, for every 0.5 seconds, the amplitude decreases by 2%. Okay. So that means what I can say here is this, right? So that means x max is equals to 0.98 of the amplitude because decreased by 2% when time is equals to 0.5 seconds. So that's the information that I'm given provided in the example, right? It means it decreases by 2%, so at a time of 0.5 seconds. That means I can use this in this equation that we just derived to solve for the tau. Because then I can say then tau is equals to, so if I'm rearranging, it will be negative t over 2 ln x max over a, like this. All right, so then this is equals to negative 0.5, then 2 times ln, then I'm going to get 0.98a over a, cancels the a, and I can then solve for the tau, okay, which will be 12.375 seconds. Okay, just plug in there and then solve for the time constant, we get 12.375 seconds. That means this is the time constant. Now, we also told that there, we want to know if the initial amplitude is 10 centimeters, what will be the amplitude after 25 oscillations? All right, so, and the time for each oscillation is 0.5 seconds. Okay, that means what we can say here is then, let's say 25 cycles, right? Or oscillations. That means, t is equals to 25 times period, and it equals to 12.5 seconds. That means, after 25 cycles, right, the time is, 12.5 seconds. So then what we do here is we can say that at this time, the amplitude will be x max equals then 10 centimeters e to the negative, remember is t over, you can see, right, is t over 2 tau. So then negative 12.5 seconds over 2 times 12.375 seconds, right? 2 times tau. And if I calculate this, I'm going to be getting 6.0 centimeters. Okay, because I use centimeters here, I'm going to get centimeters over there. That means now the amplitude is, is 6 centimeters rather than 10 centimeters. Okay, at that time. So x, at this time the amplitude will be 6 centimeters. Okay, and that's our solution for this example. All right. Few other applications of this is known as a natural frequency and driving frequency. So this is basically, when you have a system that oscillates, and everything technically has its natural oscillation. So, and vibration of the molecules always gives some, system, every system or everything around you basically have some kind of natural, oscillations. So we call it whatever frequency you have, right? That's a natural frequency. But you can also have a, what we call driving frequency, where you basically have some kind of external force, providing some kind of external, let's say, uh, frequency, right? So you can see, right, a singer or musical instrument can shatter a crystal goblet by matching the goblet's natural oscillation frequency. And that's important because, for example, in this case, if the external frequency or driving frequency, right, matches the natural frequency of the object, then you get amplification of basically this frequency, right? So then amplitude of the oscillation is then generally not very high unless external frequency matches the natural frequency. And when it happens, right, that imagine that the reason that let's say this crystal goblet, let's say shatters, is because the molecules start oscillating with much higher frequency than before, and the object cannot keep its shape anymore because of that, forced oscillation matching the natural frequency, oscillation, right? And then let's say in this particular case, you can shatter a crystal goblet by, making the molecules in the goblet, right, oscillate much, with much more violent, let's say, frequency and things like that. So this is known as a resonant frequency. So the response curve shows the amplitude for a driven oscillator at frequencies near its natural frequency. So for example, you can see right at the peak here, it represents the oscillation has maximum amplitude when those two match each other. So this is known as a resonance or a resonance frequency. That means a resonant frequency, the system oscillate, at much higher. And this is the thing, like let's say natural oscillation generally very small, but when amplitude of the natural oscillation is matches some kind of outside driving frequency, then it can be amplified much greater. So like you can see over here, right? So for example, depending on this this constant b, right? So then what we can see here is you can really amplify the amplitude of the oscillation of your system. And this can be dangerous, let's say, for example, for the things like buildings and bridges, right? So that's why sometimes you can have a picture where you probably have seen a picture of a building or a bridge, right? Especially bridges, right? When there's an earthquake or something like that, the bridge, can completely collapse on itself. That's because the bridge itself vibrated some natural frequency. And if the earthquake frequency, right, the driving force, matches the frequency of a a bridge, right? Just happens, happen to match, then the bridge can completely start, shaking back and forth. And that's basically because the, all the molecules inside the, the bridge start oscillating with a really large amplitude, and it can completely destroy the bridge and things like that. So that's why it can become dangerous. So, you know, let's say if you're an engineer or, civil engineer or something like that, this is something you want to explore even more. All right, guys, this is then completion of chapter 14.